Hey, today we're going to talk about how to analyze electrocardiograms with Python code. Electrocardiograms, or EKGs, are one of the most popular tools that doctors, nurses, and paramedics use to look at patients' hearts. Electrocardiograms look at the electrical activity of the heart, and the cool thing is, the electricity of the heart will tell you almost everything you need to know about how it's functioning. And the cool thing is, we can use Python code to analyze that electricity. If you've ever been in the hospital, or you've called 911, or you have seen Grey's Anatomy or House, you know that squiggly line that signifies a heartbeat? That's an electrocardiogram. Each little part of that squiggly line has a very specific timing and height and width to it, and whenever anything in that is off, that signifies that there could be something wrong with your heart. With that being said, please don't use this tutorial, code, any of these datasets, or related articles to diagnose yourself or others with any medical conditions. This is not medical advice. We are not doctors or nurses. Most other EKG tutorials for Python explain electrocardiograms for about 5 seconds and then immediately start talking about machine learning. We're not going to do that. We're going to talk about the actual parts of the electrocardiogram, the parts of each heartbeat in the electrocardiogram, and how each measurement of that heartbeat indicates which part of the heart is having issues. When doctors and nurses and paramedics look at an EKG, that's what they're looking at with their own eyes. They're looking at each little part of the curve and saying, okay, this part is too short, or it's too long, too wide, and that's the part of the heart that is having issues. We're going to go over the specifics of that in a second. To zoom out a bit, this video is going to be the first in a series of videos that take what doctors and nurses and paramedics do when they look at an EKG and translate that into code. We're going to use SciPy, which is Python's most popular scientific library, to both load an electrocardiogram dataset and then analyze that dataset. Long story short, we're going to use SciPy to label each part of the little squiggle of the heartbeat, measure it, and then compare it to a healthy or unhealthy heartbeat, and specifically, what type of unhealthy heartbeat. There are a few dozen types of common unhealthy heartbeats with a very specific look to them and specific measurements and changes in the sizes of the heartbeat's waves, and we're going to use Python to measure those and characterize those. What we're going to do is use SciPy's built-in electrocardiogram dataset, take a look at it, get familiar with it, and then practice labeling and analyzing it. Okay, let's get right into the code, and then the rest of this will make more sense. Let's go ahead and go to Kaggle. It's a popular data science site that gives you an ability to code in your browser, so you don't really have to mess around with a bunch of installs and stuff. So go to kaggle.com, create an account. It's totally free, and then you can create a Kaggle notebook, which allows you to code and graph stuff and see everything, code on the fly right in your browser. The first piece of code we're going to write is all of the import statements. We're going to import SciPy, NumPy, Pandas, and Matplotlib. These are all libraries that are super popular in data science. I would totally get familiar with Pandas, NumPy, and Matplotlib if you want to do just pure data science. And then if you want to do coding for science, biology, chemistry, whatever, SciPy is a need to know if you're doing Python. SciPy, NumPy, Pandas, and Matplotlib are all kind of rolled into each other. They use each other's functions to get stuff done, but we do need to import all of them. Second thing we're going to do is check the version of SciPy. There's a weird quirk about Kaggle right now where certain notebooks will import different versions of SciPy, so we're just going to make sure we have the correct one because the versions can be very different. So let's go ahead, and I'm going to rerun the import statement just to show you. It takes a couple seconds to import stuff. And then I'm going to run scipy.__version__, and that just tells us, SciPy is telling us itself what version it is. It looks like in this notebook the version is 1.10.1. If you create a new SciPy notebook today, it might load version 1.7 of SciPy. There's just a couple little statements you'll have to change to import stuff, or import or use functions later on, but we'll cover that in a second. Okay, let's take a look at this electrocardiogram. The electrocardiogram is actually stored in a function, so we're going to type EKG equals SciPy p.datasets.electrocardiogram. And if we press Shift Enter, it'll run that line. What we're going to do is look at what just got stored in the EKG variable. So I'm going to make a new code chunk, just type EKG, Shift Enter, and it shows us that we just got back electrocardiogram data. These little numbers right here are actually the voltages of each little heartbeat. And I will show you what the heck that looks like right now. So we have our EKG data. It shows all of the voltages of the EKG. Each value is actually a y-axis value of the squiggle of the electrocardiogram. So what we're going to do now is plot it. We can't plot it right away. What we're actually going to do is take this array and convert it to a pandas object so that we can plot the pandas object using matplotlib. It's actually just 2 lines of code. So we're going to do EKG equals, and this is going to convert it to a pandas series, pd.series EKG. And that will convert the EKG to a pandas object. See, there were no errors there, and then we can just do EKG.plot, and plot is the matplotlib function. And there is our EKG. This is actually, according to the SciPy documentation, this is 5 minutes worth of heartbeats from one person. It doesn't look like much right now. It just looks like a bunch of squiggles. It's like a big blue blob. But if we zoom in, we'll start to see heartbeats. So to zoom in, all we have to do is just take a chunk of the EKG and plot that. One thing we can find out by reading SciPy's EKG dataset documentation is that it happened to be collected at 360 hertz. So there's 360 data points per second. That means that if we use the EKG array and we just collect, we do 0 to 360 as an index, that gives us 1 second of EKG data of the whole 5 minutes. So if we want to see a couple of heartbeats, maybe that's 2 to 3 seconds. So we can preview that right now. We can do EKG, and then we'll go from 0 to, we'll do 3 seconds. So 3 times 360, let's see, 900, 1080. So we'll do EKG 0 to 1080, and this will show us 3 seconds worth of EKG data. And then we'll just plot that. Alright, so this shows us 5 heartbeats with a bunch of little squiggles. Okay, so these are 5 heartbeats. We're going to start talking about what the heck these heartbeats tell us. What is the EKG really telling us? Actually, let's zoom in even further. I'm going to zoom in on just pretty much one heartbeat, so that this makes more sense. Alright, so this is one heartbeat and then kind of the start of another heartbeat. But what are we really looking at here? It seems like when you see people's representations of heartbeats, it's just like a line with a squiggle, and any sort of squiggle makes sense. But actually, in a heartbeat, every little curve is monumentally important to telling you how healthy your heart is. Each heartbeat in an EKG actually has a specific name. We call it a QRS complex. That's named after pretty much the alphabet letters that we use to talk about and label the whole heartbeat. We have a P wave. Each of these is called a wave. So we have the P wave, the Q wave, the top one is the R wave, that's the big one, then the S wave, then the T wave. Each part of this has a specific size and width that it's supposed to be, and if it's bigger or smaller than it's supposed to be, that's a problem. That's probably deadly, actually. So let's go back to our actual data set. This is a real electrocardiogram from a real person. That is an excerpt from a famous MIT arrhythmia dataset. Arrhythmia meaning times when the heart is beating a way it should not be. This right here, this is the whole QRS complex we just looked at. We have, to start, this little T wave, a little dip for the Q wave, and then the big R wave. It spikes up, comes back down to the S, and then nothing, and then a T wave. So like the P and T waves kind of look the same, and then you have the big R wave in the middle. If we go back to our data set in Kaggle, that's really what we're looking at. This little bump right here that starts kind of around index 50 on the x-axis, that little bump, that's the T wave. And then the little dip right before the big R wave peak, that's the Q wave. And then of course the big peak, R wave. and so on and so forth. And then this little, around 200, that is the T wave. And then you see the next heartbeat, the same thing. That's the P wave, the little Q wave, then the R wave jumps up. So each heartbeat in this data set really has very specific parts that need to happen just so to indicate a healthy heartbeat. As a preview, let's take a look at some arrhythmias, or bad heartbeats, bad EKGs. Bad EKGs, typically they'll have an R wave or something, but then there's a lot of junk that happens in the middle. This isn't always the case, but honestly, for example, this is atrial flutter. It kind of looks similar to a healthy heartbeat, but there's actually a lot of junk going on in here. Let's quickly look at some really ugly bad heartbeats to show you what it looks like when things go wrong. There are a few dozen common types of arrhythmias, and each one of them signifies some sort of electrical signal that's not getting to where it needs to be, and then some muscle that's not squeezing the way it needs to be, meaning that blood does not get to where it needs to be. For example, here's a type of arrhythmia where the P wave is actually not able to kick off the rest of the heartbeat. If you see the big QRS complexes, you see the R wave spike, but then you'll see these kind of lonely P waves that either it takes them a while to kick off the heartbeat, or they are lonely. Like you see this one, the T wave happens at the end of the QRS complex on the far left of this EKG right here, and then right after it a P wave happens, but then no heartbeat happens after that. And then it takes a whole nother cycle before the P wave is able to successfully kick off the rest of the heartbeat. Arrhythmias tend to look like this. They'll have some portion of the spike, but it'll be exaggerated, or it'll be too wide, or waves will be missing, or there'll be extra waves. So our code is pretty much going to characterize the waves by measurements. Unlike other tutorials, we're not going to talk about machine learning. We're not going to talk about convolutional neural networks. We're going to say, hey, this wave is here. It is this size and shape, and then it's followed by this wave, which is this size and shape, and that indicates possibly this type of heart disease. It's going to be very straightforward and rote. If you want to check out more of this game and arrhythmias, I will link to it in the description. What is the QRS complex actually telling us then? There's some squiggly lines and waves, but what does that say about the heartbeat? What an EKG is doing is looking at voltage traveling through the heart. These yellow lines are neurons. Basically, when a heartbeat kicks off, it starts at this green part. This is the sinoatrial node, or the pacemaker of the heart. The natural one, not a device. And it starts there, and then it travels down the yellow lines, and then back up the sides of the heart. So really what we're seeing, when we go back to the QRS complex, that P wave, that's the first pacemaker kick. The sinoatrial node, this green part right here, that is the P wave. Here's another example. We have the P wave kicking off. That is the atria contracting or depolarizing. You'll hear the words depolarizing and repolarizing a lot with cardiology and neurology. Depolarization is really just a neuron kicking off, and then repolarization is the neuron resetting so that it can get ready to kick off again later. So what's really happening here is the P wave is kicking off the first start of the heartbeat, the atria are contracting, and then the big center, the R wave, is the ventricles, the largest part of the heart, the part that's actually going to squeeze so hard that it sends the blood to the rest of your body and to your lungs. That part is happening, which is also why the R wave is so big, because it's the strongest part of the heartbeat. And it has to be, because it takes so much more energy to pump blood from the heart out to, down to your feet, down to your arms, down to the rest of your body. That needs a big squeeze. And then the T wave is just everything resetting or repolarizing. If you want to learn electrocardiograms more in depth, Ninja Nerd has a great video on the basics of electrocardiograms. He talks about the electricity of the heart from an engineering perspective in a way that you will definitely find useful if you're a programmer or if you have an engineering background. So we have all of these waves with special letters for names. What do we do with that in the code? What we're going to do is use SciPy, specifically SciPy's find peaks function, to find and label all of these waves according to their height and position. The easiest example of this is we're just going to take every gigantic spike over a certain height and call that an R wave. And then we can use each R wave to determine how fast the person's heart rate is. Right here I have some code that takes 3 seconds worth of EKG data, just the first 1080 data points, and then plots it. So this code is just EKG index 0 to 1080 dot plot, and then we give the plot a title, plt.title, 3 seconds of EKG data. Press Shift Enter, and then it plots that. Now we can use SciPy's find peaks function to label each of the R waves. So we're going to write R waves equals, actually we're going to write R waves comma metadata, because the find peaks function is going to return two things: the R waves, the indexes of the R waves, which is just numbers, and then some metadata that tells us a little bit about the R waves, which we don't necessarily need to use, so we're going to kind of throw it away for a second. So we're just going to have R waves comma metadata equals scipy dot signal dot find underscore peaks, and then we are going to give it our EKG data, EKG index 1080, and then we're also going to give it the height. This is going to be the cutoff height that tells find peaks, okay, peaks above what threshold? Because if we don't give it a threshold, it's going to consider every little jagged edge on this graph a peak. So we want to tell it probably, hey, anything over 1.0 on the y-axis, that's going to be an R wave. So we can say height equals 1.0, and then we will run that. And now let's see what the variable R waves holds. It holds, see, we got 5 numbers right there. We have 5 heartbeats in the graph above. So this just tells us the index on the x-axis. Hey, where are these R waves? So that looks about right. The first number is 125, and yeah, I'd say roughly at index 125, we got an R wave peak, and then likewise around index 343. Yeah, that's the other R wave, so the numbers track. So now we can actually visualize the R wave peaks that we just found by layering them on top of our last graph. So what we're going to do is make a brand new graph, but basically the same as the last one. Take the first 3 seconds of the EKG, dot plot, and then, dot plot, and then we will do, to add another layer, we'll just do plt.plot, and then we'll give it the indices of the R waves. So when you do plt.plot, it's expecting an x and a y argument, right? So the x is going to just be the indices, this array right here of the R waves, and then we're going to actually, and this is a little weird, we're going to do EKG 1080 and then say the R waves of that. So it's going to be the first, you know what, actually this is going to be a little easier. If I just go up here, I'm going to relabel these. I'm going to say 3 second EKG equals, what I'm going to do to make plotting easier is to store the first 3 seconds of the EKG in its own variable, and then the rest of this will make more sense. So 3 second EKG equals the first 3 seconds of the EKG, EKG index 0 to 1080. And note, you can put the 0 in the index or you can leave it out. It's optional. When you are at the very first element or the very last element of an index, you can just leave it out. It's implicit. So what we're going to do is assign the EKG chunk to 3 second EKG, and then we can do 3 second EKG dot plot, and that'll make the exact same graph as we saw above with the 5 heartbeats. And then we can layer on top of that the R waves. So X is R waves, and then Y is actually 3 second EKG with the indices. It's actually the values of 3 second EKG at these R waves. It'll automatically pluck out the correct values. And then we're going to say that our marker on the graph, visually, it's going to be an X. So whenever there's an R wave, we're going to mark it with a little X. It's going to be orange or red or something. And then we'll give it a title, plt.title, labeled R waves, or 3 second EKG with labeled R waves, and we'll see if that works. And there it is. We have the regular chunk of EKG that we just had, but there are these little orange X's at the very top of the graph, and those are our R waves. Okay, that is all for today. In the next video, we're going to go over how to use the same function, find peaks, to label the P wave, the T wave, and the Q and S waves, and then measure those and find out what they're really saying about how healthy or not healthy this patient's heart is. Thank you for watching. Please let me know if you need anything to be more clear, if something didn't make sense, or if there's a specific thing about the heart and coding that you would like me to explain. Thanks.